Until recently, scientists were almost ready to give up on finding the graviton. Despite nearly a century passing since its existence was predicted, the calculations consistently showed that the path to its discovery would be a long one. But earlier this year, in 2024, a research paper was published in the prestigious scientific journal Nature. The paper discussed a proposal by a team of scientists to conduct a specific experiment, an experiment that, they claimed, could finally solve the mystery and lead to the discovery of the graviton. It said that even though there's still more than 3/4 of this century left, if this experiment succeeds in detecting the graviton, it would undoubtedly be the discovery of the century. No other breakthrough in physics, not even solving the mysteries of dark matter and dark energy, would match its significance. Even proving the validity of string theory or any other theory unifying physics would pale in comparison to uncovering the graviton. Yet, despite this monumental importance, the experiment proposed in the paper has been delayed and remains the subject of heated debate. So, what exactly is the graviton? Why is it so significant? And why has the experiment that could solve this dilemma been postponed? Grab your favorite drink, get comfortable, and join us as we dive into this fascinating topic. And don't forget to subscribe, like, and share the video. Let's aim for 3,000 likes on this episode. Welcome to another exciting installment of Unveil the Universe. Our universe operates under 4 fundamental forces of nature: gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. But for now, here's what you need to remember. Scientists have already discovered the particles responsible for mediating the other 3 forces. These are the particles through which the forces exert their influence and whose existence proves the presence of the forces themselves. For the strong nuclear force, we have gluons. For the weak nuclear force, we have the W and Z bosons. And for the electromagnetic force, there are photons. However, gravity remains the only force without a known mediating particle. The particle associated with gravity, known as the graviton, has yet to be found. Mathematically and theoretically, it's believed to exist, and physicists have even named it in anticipation of its discovery. The name chosen for this elusive particle is the graviton. This, in short, is the graviton, one of the most eagerly awaited discoveries in physics. So significant is its potential discovery that scientists have already included the graviton in the standard model of particle physics, despite not having observed it yet. They are that confident in its existence. The theory of everything is a concept that physicists have long dreamed of, a framework that unifies all 4 forces of nature into a single, cohesive mathematical model. In other words, it's a theory that bridges general relativity with quantum mechanics. The theory of everything is a broad term that could refer to any theory capable of achieving this unification. String theory, and specifically superstring theory, is one such model that claims to meet these requirements. However, these models still contain many unknowns that need to be resolved before their validity can be confirmed. One of the most critical unknowns is the graviton. This is why the discovery of the graviton is seen as more crucial than proving any specific theory of everything. Its discovery would be the first step toward evaluating the validity of such theories. Without understanding how the graviton works, it's impossible to judge whether any unifying theory is correct. In simple terms, discovering the graviton is the cornerstone of progress in this field. It's like asking whether a high school diploma or a PhD is more important. While a PhD is undoubtedly prestigious and opens many doors. The high school diploma is essential because it's the foundation that leads to the PhD. In brief, dark matter is an invisible form of matter that influences gravity, while dark energy is a type of energy driving galaxies apart and accelerating the universe's expansion. Both remain enigmatic forces in physics, but the graviton might hold the key to understanding them better. To simplify things, we can say that the universe, my friend, consists of two types of matter and two types of energy. First, there's ordinary matter and ordinary energy. These make up everything we know, from atoms to galaxies. Then, there's dark matter and dark energy, about which we know virtually nothing except for the effects they produce. For instance, dark matter cannot be seen or detected using telescopes. It's thought to be a type of matter that neither absorbs nor reflects any light. Its presence is inferred through its effects and logical mathematical calculations. To make this concept easier for those unfamiliar with astrophysics, scientists often use the analogy of placing a small apple on one side of a scale and finding the scale indicating a weight of 5 kilograms. If you're certain there's no malfunction with the scale, then there must be something invisible alongside the apple causing the added weight. Similarly, astronomical calculations consistently show that the known matter and energy in the universe account for only about 5% of its total mass and energy. This discrepancy suggests that either our calculations are wrong or our understanding of gravity is incomplete. In other words, there may be an issue with the scale we're using to measure. For example, the stability of stars within galaxies requires a force to support gravity. According to our calculations, gravity alone is insufficient to hold stars within galaxies. Scientists are divided between two possibilities: higher than expected rotational speeds of stars around galaxies, or the existence of dark matter and dark energy. It could also be a combination of both explanations. Regardless of the correct explanation, the conclusion is the same. There's a fundamental flaw in our understanding of gravity. So, no matter how much we explore alternatives, we'll still need to discover and understand the graviton. In fact, finding and studying gravitons might eliminate the need for the dark matter and dark energy hypotheses entirely. In other words, discovering the graviton could solve multiple mysteries at once. Firstly, it would give us a more accurate understanding of gravity in general. Secondly, it would reveal how gravity works on a quantum level. Thirdly, it would help us solve other puzzles such as dark matter, dark energy, black holes, and the early universe. Solving these mysteries requires a combination of general relativity and quantum mechanics, but the delayed discovery of the graviton has stalled progress in all these areas. This is why scientists consider the graviton's discovery to be a top priority. But the critical question remains: what's holding back the experiment that could uncover it? Let's start with the basics. Even if we had a detector for gravitons, the process of utilizing it would likely be extremely challenging. Experiments would need to be repeated multiple times to ensure the accuracy of results. This is because, based on our current understanding, gravitons interact very weakly with ordinary matter. In fact, their interaction is believed to be far weaker than that of neutrinos. Neutrinos, often called ghost particles, can pass through enormous amounts of matter without interacting. They are incredibly small, elementary particles that move at incredibly high speeds. Now imagine physicists affirming that gravitons are even more elusive and complex than neutrinos. Conducting an experiment to detect such particles would not only be incredibly intricate, but also require enormous funding. And that's not the only hurdle. There's another major obstacle: the cooling systems necessary for the experiment. Extreme cooling is a crucial requirement for such experiments, adding another layer of complexity and cost to the process. Despite these challenges, the potential rewards make the effort worthwhile. Finding the graviton could transform our understanding of the universe and solve some of the most profound mysteries of modern physics. The question now is, how long will it take before we overcome these obstacles and conduct the experiment? Before I dive into the cooling problem, let me clarify something, my friend. The delay in conducting the experiment isn't caused by scientists. In fact, even skeptics of the experiment's feasibility are eager to see it happen, if only out of sheer curiosity. The real reason for the delay lies in obtaining government approval for the necessary funding. Scientific ideas and research projects don't always receive sufficient financial backing, and this particular experiment is a prime example. It essentially requires building a small asteroid-like structure to serve as the graviton detector that scientists would rely on. The plan involves creating a massive object weighing at least 1 ton, designed from a special composition of metals and elements. This object would then need to be cooled to the lowest temperature possible, approaching absolute zero, which is the coldest temperature in the universe. On top of that, the experiment demands replicating many of the conditions of outer space in a controlled laboratory environment. The goal of all this? To create the perfect conditions for gravitons to manifest. Massive objects are essential for highlighting gravitational effects because the distortion in space-time fabric becomes more apparent with increased mass. With this approach, larger numbers of gravitons are expected to become active, generating a gravitational wave that would impact the object, producing measurable vibrations. In an ideal scenario, the experiment might even allow scientists to directly detect a graviton. But grand as this ambition may be, it's clear the experiment's complexity and costs are monumental. And putting aside the graviton itself for a moment, the most pressing question now is about cooling. Can scientists truly succeed in cooling such a large and massive object to temperatures near absolute zero? The cooling process is one of the most challenging hurdles preventing this experiment from moving forward. In fact, doubts about achieving the required cooling levels for an object of this size have even drawn skepticism and humor from some scientists. They joke that if the research team manages to solve this problem, they should immediately collaborate with companies like Google and IBM. This is because quantum computers face a similar challenge: cooling large systems. Quantum bits, or qubits, the fundamental units of quantum information, are extremely sensitive to heat. Even a slight increase in temperature can cause quantum states to collapse or degrade. Controlling qubits at extremely low temperatures is already a highly complex task. So you can imagine how much more difficult it would be for the team conducting this experiment to cool their asteroid-like object. Achieving such extreme cooling requires a highly advanced thermal insulation system to minimize heat transfer from the surrounding environment. Even the tiniest amount of heat leakage can prevent the system from reaching ultra-low temperatures. Generally, the smaller an object is, the easier it is to cool, as smaller objects contain less heat that needs to be removed. However, larger and heavier objects, like the one required for this experiment, possess significant thermal energy that must first be extracted. This significantly increases the experiment's duration and costs. Moreover, the advanced cooling technology required is among the most expensive in the world. It's hard to imagine how governments could be persuaded to allocate such substantial funding for an experiment that some scientists doubt will even succeed. Do you think this experiment will ever be conducted, especially since it has been mentioned in one of the most prestigious scientific journals? Let us know your thoughts in the comments. If you've made it this far, it means you've enjoyed the video, so don't forget to give it a like. As always, I'll leave the sources in the description. See you soon in another exciting and informative video.